Hi, this is Mrs. Baisden, and today we're going to talk about Hess's law and determining enthalpies of reactions. So when you're looking at a chemical equation and the heat of reaction or the enthalpy of reaction that's associated with it, we talked about how when that heat of reaction or enthalpy of reaction is given, it's per mole of reactants or products in the given equation. If you multiply that chemical equation by some factor, then you also have to multiply the delta H. If the chemical equation is reversed, then you reverse the delta H value or change the sign of delta H. Or if you can express the chemical equation as a sum of a series of steps or intermediate steps, then the delta H of reaction for the overall equation is the sum of all the heats of reaction for each step. So we're going to use something called Hess's law to determine the overall enthalpy of a reaction. So Hess's law says the change in enthalpy for a stepwise process is the sum of the enthalpy changes of all of the steps. So you can see the overall delta H of that reaction A to E can be given by the overall equation A to E, or you can take the heat of reaction for A to B, B to C, C to D, and D to E and add those up, and that will give you the same value. So the best way to learn how to do these is to actually do some example problems. So this is almost like a logic puzzle. So the way these will be presented is it will give you the overall reaction. So that's what they're going to give you first. With that overall reaction, they will also give you the intermediate steps. So these three reactions that are given can all be rearranged so that they add up and equal that overall reaction. They've given us the delta H of reaction for each of those intermediate steps. So once we've rearranged those and done the appropriate things to the delta H value, then we can solve for the overall delta H of that reaction. So what we're trying to find here is we're trying to find the delta H of this overall reaction using those three intermediate steps. So as you go through this is going to be very easy for some people, and then other people struggle a little bit with this. Just kind of depends on how your brain works. Some people are able to see this very easily. Other people, it's a little bit of a struggle until you get the hang of it. So be patient with yourself as you're working through this. And if you don't feel like you're getting it fast enough, that's okay. Everybody comes to this at their own pace. So be patient, work through it, do lots of examples, and eventually you'll get it figured out. So when we're looking at this, the best way to start is to look at what the reactants are and what the products are. And then look and see what the reactants and products are of the equations that they give you. So remember things we can do to them. We can reverse a reaction. If we reverse a reaction, we have to change the sign of delta H. We can multiply the coefficients by some factor. If we do that, we also multiply the delta H value by that same value. We can divide by some number, and then we do the same thing to the delta H. Then once we have all of those adjusted and we add them all up, then we add all the delta H values up as well. Okay, so for this first one, we can see that I have C3H8 as a reactant on this one, but I need it to be a product. So I'm going to rewrite that first equation so that the C3H8 is a product. So then what I have to do is I have to reverse the sign. So now I'm going to make this positive. Okay, then I'm going to look at the next one. So I have carbon on the left. These other ones I'm not going to worry about because you could potentially have things cancel out. So if they're not in the overall equation, then they're going to have to cancel out, and that usually takes care of itself on its own. And I have carbon as a reactant here. But I have 3 carbon here. This equation only has 1. So what I'm going to do with that equation is I'm going to multiply this whole equation times 3. So then this becomes 3C plus 3O2 gives me 3CO2. So then my delta H of reaction equals negative 393.5 kilojoules. I'm going to multiply that by 3. For my last equation, I have 2 H's, and then I have a couple other things that are not in the overall equation, but I need 4 H2's. So on this one, I'm also going to multiply this by 2. So I'm going to have 4 H2 plus 2 O2 gives me 4 H2O. So for the delta H for this one, it's going to be negative 483.6 kilojoules times 2. So then when I add everything up, anything that's on the same side of the yield sign, I'm going to add. If it's on opposite sides of the yield sign, it can actually cancel out. So CO2, and you can cancel things before or after. So I like to cancel before, but if you want to wait till after you've got it all at the bottom, you can do that as well. So you can see here, this 3CO2 and this 3CO2 is going to cancel. The 4H2O is going to cancel. And then I have 5 oxygen over here, and I have 3 plus 2 over here. So this 3 and this 2 will cancel out that 5. So then I'll bring everything else down. 3 carbon plus 4H2 gives me C3H8. And notice that this equation is the same as the equation that I was asked to find at the beginning. And then all I have to do is modify my delta H values. So this one I already modified, this one I multiply by 3, this one I multiply by 2, and I'm going to add all of those up. That'll give me my overall delta H of reaction of negative 105 kilojoules. So that's my overall answer for that particular question. Okay, so let's try another one. So for this one, I went delta H for the reaction that's given. They give me the intermediate steps that I can rearrange to get that overall reaction. So on this one, I have NO on the left, but I need it to be on the right. So for this one, I'm going to reverse this for now, then I'm going to worry about the coefficient later, because you can see that the coefficients are different, but we're going to worry about that later on. So I'm going to change this to 2NO2 goes to 2NO plus O2. And then because I reversed it, this is going to become a positive. Second one, the N2 and the O2 aren't in the overall equation, so I'm going to focus on the NO. So that one is also a product, so I'm going to leave that as it is. And then I may need to do something to that, but I'm going to rewrite it. But leave it as written. And then for my last one, I have N2O and then N2 and O2, which are not in the overall equation. So N2O is on the right side, except I only need one of them. And that N2O is nowhere else in the equation, so I know that's the only place I can get the N2O. So I'm going to divide this equation by 2. So I'm going to make this N2O goes to N2 plus 1/2 O2. So for this H of reaction, this one I'm going to divide by 2. Okay, so the last thing I need to do, I've got the N2O in the right place. I have that 2, I only need one NO2, but I have 2 of them here, and I need 3 NOs, and I have 2 NOs and 2 NOs here. So if I only need one of these NO2s, I know I'm also going to divide this by 2. So what that's going to do is that's going to make those 1, and then it's going to make my oxygen 1/2. And we'll see how that actually helps us in the overall equation here. Okay, so my overall changes that I made here is I divided this first one by 2, but I also flipped it, and I already took care of that. Second one, I left the way it was. Third one, I divided by 2, but I left it in the direction that it originally was. So now I can add all of these up. So I'm going to eliminate anything that's on both sides first. So I have an O2 here, and this half cancel out that one. I have an N2 here that cancels out this one. And again, you can cancel things that are on opposite sides of the yield sign. So that's why those NOs or those N2s can cancel out. Then I'm going to bring everything else down. N2O plus NO2. And then I have 2 NOs plus 1 more. That gives me 3 NOs. To get the overall heat of reaction, I'm going to divide this by 2, add it to the 182.6, add it to the negative 163.2 divided by 2. So I'm going to add all of those up after I make the adjustment, and my overall should be 157.55 kilojoules. Okay, so a lot of this could be trial and error. You may want to use a whiteboard when you're practicing these, so you're welcome to use the whiteboards in the classroom, or give yourself lots of room on scratch paper when you're working these out, because sometimes if you get too far gone on these, you have to erase everything, and the best way is just to go back and start over and take a different path than what you did that got you to where you weren't headed towards what you wanted. Okay, so a little bit confusing at first, but once you get the hang of it, they're really not that bad. Just think of it kind of like a big puzzle. You have to rearrange all those equations to get them to add up to the overall equation, make your adjustments to the delta H values, and then you add them all up. So before we look at the other way that we can calculate the overall heat of reaction, there's a couple of things we need to talk about. So standard state is a state that is defined for different states of matter. So standard state for a gas is considered exactly 1 atm of atmospheric pressure. If it's a liquid or a solid, the standard state is the pure substance in the most stable form at a pressure of 1 atm and a temperature of 25 degrees Celsius. And if it's a substance in solution, the standard state is exactly 1 molar. The reason that we need those values is because when we're looking these values up, if something is in its standard state, then it has a standard enthalpy of formation of 0. And that's important to know because those are ones that will not be provided when you do this other method. So if we look on here, this is what we mean by standard state. So calcium is a solid. That would be its standard state. So its standard state, the enthalpy of formation would be 0. Cl2, this is the normal state you would find chlorine in. Standard state is 0. H2, you can see the standard state is 0. N2. So the state that you would normally find something in, that's considered the standard state, and that value again is 0, and that's going to make a little more sense here in a minute. The only one that's a little bit weird that you have to remember is carbon. So carbon solid is standard state, but graphite is considered standard. Diamond has a small enthalpy of formation. So if it's given as graphite, you know the value is 0. If it's given as diamond, then you know that there's a value, and that would be provided. Okay, so what this is asking us to do is to write equations for the formation of the following compounds from their elements in their standard states, and then include the value for the heat of formation. So the heat of formation, this is going to come from that table that we just looked at. Okay, so what this is asking us to do is this is just asking us to kind of think through what an equation would look like if we were talking about how this substance was formed. So if I want to form magnesium, I would need magnesium from its elements. Okay, so this is not a reaction like we've done in the past where we're reacting two substances. We're thinking about if we want to form magnesium carbonate from its elements, what would that look like? So we would have to have magnesium, we would have to have carbon, and we would have to have oxygen. And then when we talk about standard states, magnesiums would be solid, carbon would be solid, O2 would be gas. And then those would make MgCO3. So if we looked at this, to balance this, we would have to put a 2 here, a 2 here, and a 3 here. And then that would give us 2 of these. When we're writing equations for formation, we want those to be per 1 mole of that product. So what we would have to do then is we would have to divide all those coefficients by 2, because when you look those values up on the table, those are all given per 1 mole of the substance. So I would actually write this as Mg solid plus C solid plus 3/2 O2. So this is now a point where we can have fractions in our balanced equations, MgCO3. So that's the only way to get that to be 1 mole. So then if we go back to that table and look up the value, the heat of formation is negative 1095.8 kilojoules. Okay, same thing for this one. For glucose, I need carbon. Hydrogen in its standard state is H2. Oxygen is O2. And then that would give me C6, H12, 0.06. Then if I balance this one, I end up with 6, 6, and 3. And that one, by balancing it, it does end up with that already being 1, so I don't have to make any adjustments there. And then if I look up that heat of formation value on the table, that would be negative 1,273.3 kilojoules. So this isn't asking us to solve anything really, it's just asking us to write out those equations. So when you do these, it's important to put the states of matter, because you'll see that the state of matter does determine what value you're going to use when we start doing the next section, and you have to do calculations with them. Okay, so this is the other way we could calculate a heat of reaction. This is a summation equation. So what you can do is you're going to subtract the enthalpies of formation of the reactants, multiplied their stoichiometric coefficients, from the enthalpies of formation of the products, multiplied by their stoichiometric coefficients. So basically what that says is I'm going to take all the heats of formation of the products minus all the heats of formation of reactants. That's what gives me the overall delta H. So the delta H of reaction is for the whole thing. A delta HF, or delta H formation, this is a value that's going to come from a table. So that delta H of formation, you're going to look those values up, or those are going to be given, and then this overall heat of reaction would be calculated. The only time the heat of reaction wouldn't be calculated would be if they were forcing you into solving for one of these heats of formation, and they would give you the overall. So you'll see when you do these problems, you'll be forced into one method or the other, depending on what information is given in a particular problem. So this just means the sum. So that means I'm going to take the coefficient times the heat of formations of products minus the sum of all the coefficients times the heat of formation of the reactants. And again, these make a little more sense once you actually go through and do some practice problems. Okay, so this one says, use standard enthalpies of formation to determine the H of reaction for the reaction given. So notice there's a table down here that has some information on it. So I would need that in order to solve this particular equation. So to get the delta H of reaction, I'm going to take the sum of all the delta H's of products minus the sum of all the delta H's of the reactants multiplied by their coefficients. Okay, so what that means is I'm going to look up, so it's always products minus reactants. I'm going to look up NO, and that value is 91.3, and there's 4 of them. So I'm going to use brackets here to keep my sections separate. So I have 4 times 91.3 kilojoules, so that's where this came from, plus 6 times H2O, which is negative 241.8 kilojoules. So those are all my products. Now I'm going to subtract those from my reactants. So 4 times NH3, negative 45.9, plus 5 times 0. So notice O2, a gas, oxygen is a gas in its standard state. The value of delta H of formation is 0. So sometimes they will give you those. Sometimes they're going to expect you to know that. So if you see an element that's in its standard state, then you can make the assumption that the heat of formation for that particular substance is 0. And again, you'll see that as you go through and do more practice problems. So then all I'm going to do here is do the math for this. So probably the hardest part of this is getting the math correct. So make sure you show all of your work. And I'm going to give you kind of an intermediate step here so you can double check as you're working. So that would give me negative 902.0 kilojoules is my heat of reaction for this particular equation. And again, this is specific to the coefficients that are in that given equation. That's why we have to multiply by those coefficients when we're doing that equation. Okay, one more. It says a city of 100,000 people uses approximately 1 times 10 to the 11th kilojoule of energy per day. Suppose all of that energy comes from the combustion of liquid octane, which is given. So calculate delta H of reaction for the combustion of 1 mole of octane. Okay, so the way it's given, this is per 2 moles of octane. So there's 2 ways we could approach this. We could reduce those coefficients first and then put these into that summation equation, or you could do it as is and then divide the answer by 2. I'm going to go ahead and get rid of those coefficients first. So again, the reason I'm doing this is because this is asking per 1 mole, not per 2 moles as written. So I'm going to divide all those coefficients by 2. So that's where these coefficients are coming from. Then I'm going to do the same process that I did before. So to get the heat of reaction, I'm going to take the heat of formation of all the products, multiply by the coefficients, minus the reactants, using the data that they gave me. And this, when you're doing these homework problems online, sometimes they'll give you the table in the problem itself. Sometimes it might force you to go to your textbook in the back of your textbook and look those values up. Okay, so for my products, I'm going to start with CO2. So there's 8 of those, times negative 393.5 plus 9 times negative 241.8. So those are my products, minus reactants, C3H8. There's 1 of those. And then O2, element in its standard state. And make sure you write this in here, even though you know it's 0, don't leave that out because that helps me when I'm going through and grading it. If something would happen with the math on this, I would be able to see that you at least set it up correctly. So even though we all know this is going to be 0, I still want you to include that in the problem itself. Okay, so then this ends up being negative 5,324.2 minus negative 250.1. So the overall heat of reaction is negative 5,074.1 kilojoules, and that's how much energy is released, and that's what that negative sign is telling us. Okay, so very similar to that previous problem, you're given the heats of formation, and you're using the heats of formation to calculate the overall heat of reaction. The way you'll be able to tell the difference between this type of problem and the Hess's law problem is this problem is going to give you heats of formation as information or data to use, whereas the other one is going to give you those intermediate reactions to use. Okay, so then using that information we just solved for, now we want to know how many kilograms of octane are necessary to provide that amount of energy. So it said in the previous problem that many people uses 1 times 10 to the 11 kilojoules of energy per day. And I want to use how many kilograms of octane would be necessary. So I know from the previous problem that heat of reaction, once I change this to 1 and divided all these by 2, the heat of reaction per 1 mole was 5,074.1 kilojoules released. So that's why we're making it negative. So then if I want this many kilojoules, I know that I have 5,074.1 kilojoules released per 1 mole. And negative on this one, because we're solving for kilograms, I can get rid of the negative because I'm not going to report kilograms as a negative value, but I'll put it in that first step just so you can see that that's where that came from. So then this is moles of C8H18. Then I can get rid of moles and change it to grams because my end goal is I want to be in kilograms here. So 1 mole is 114.22 grams of C8H18. That's just the molar mass. And then 1 kilogram is 1,000 grams. So this is by solving for this heat of reaction per 1 mole. And again, the reason I scribbled that out is because on the previous problem, we solved for 1 mole, not for 2 moles. You would use 2.3 times 10 to the 6th kilograms of C8H18, which is octane per day. So this is how much octane you would need to power this city per day. Okay, so you're going to do some practice. The Hess's Law practice that's in your packet. You can use your online homework problems, and then we will review all of this stuff when I see you guys again on Monday.